Thank you very much for kind introduction. Good afternoon, everybody. First of all, thank you very much for inviting me to the prestigious university. I'm very pleased to be here. So my talk today already is introduced, but in the chemistry application of PCP and MOF. That is just a structure of a small pore, small size of nanospace. So if you are not the chemist, it's difficult to follow the compound. Just look at the structure. Okay. So let's go. So this is very important. In the 19th century, the human created a new technology that consumes a lot of energy. That time, human used the solid coal. In the 20th century, as you know, in the petroleum, the liquid. What about 21st century? I think that is gas substance. So this technology developed. In the case of solid, just you press it on the ground. But in the case of liquid petroleum, we need to have a vessel. In the case of gas substances, you have to have a pressurized the vessel. Okay? So the technology should be going up and up. But the problem is, humankind is still not in control of gases. That's a big issue. So these are gas substances, as you know. They are strongly connected to the environment and natural resources and energy, even in the case of life. So gas substances are very important for our life. So nowadays, in the underground resources, in the petroleum, of course, in natural gas, and in the China is a big land, you can get this in petroleum and gas substances. But in Japan is a small island, small country. It's difficult. So what we should do, and also the global warming using the underground the resources. So a good scenario is we have to use the ubiquitous material. Ubiquitous means we can find everywhere. You can get everywhere. This is ubiquitous. So for instance, in the air contains the carbon, oxygen, nitrogen, and even in the case of hydrogen. So your body constructed from the proteins, amino acids. So the air contains most of the elements. And everywhere you can take. So this kind of scenario is fantastic. So, but anyway, just look at the current status, in particular in the CO2. You are familiar with the CO2 global warming. In this case, in the year here, and this is the concentration of CO2 in the air. So, and just after the industrial revolution, I told you, the abrupt increase of the CO2 up to 400 ppm and more. So that's a big issue. So a little bit old data, but 40 billion tons per year produced. Why so? Just look at this one. If you can understand this. And we have the one loaf of bread, the 800 grams. So, and this is nature plant paper. They just analyze the whole activities to get this one loaf of bread. So this is the fertilizer and cultivation and transport and make flour and baking and something like that. All operations, we produce the 0.6 kilogram CO2. So that equal to the 327 bottles of 1 liter, 327 bottles we produce. That means we cannot escape production of CO2 for our life. So this is the scenario here, and the many CO2 produced every day. So what we should do? Do nothing. that means you have no future. I'm okay, I'm old person, but young people, you have many problems. Okay, so what we should do? But in energy issue, the nuclear power plant is also one of the way, but still the human cannot solve the issue of the waste of this in the radioactive waste. And also sometimes happens, for instance, in Japan, we have a very, very big accident. And so the other thing is CO2 capture. CO2 capture is the ideal way. So if we can do this, and this is the CO2 and O2, nitrogen, humid, H2O. So when we capture the substances, so for this, we need to have the very efficient separation system. And then obtain the substances and concentrate and store. And also using the renewable energy and water, we should convert these gas substances to the useful feedstock, methanol and the hydrocarbon or something like that. And once these materials are combusted into the air, once again, we make this cycle. So this is very good scenario, but right now it's a very hard task. But anyway, we can think this is a sort of the air is invisible gold. Okay? So now we are standing gas age. Real gold is just a gold you like, but in the black gold is coal and the petroleum. The next one, air gold. So we have to have the air gold age with the high technology. However, there's a big issue to handle gas substances. These gas substances easily diffuse. So mostly they are invisible, and they have a short life and toxic in certain cases. So to handle these gas substances well, the porous material is very important. Okay? And so by using the separation, storage, conversion, these processes should be done in the low energy process in the mild condition. Okay? So just look at the history of porous materials. As you know, in the 3,500 years ago, Egyptian era, the humankind used the charcoal. This is the porous materials. And they use these materials for medical treatment and also the other purposes. So this was written in the papyrus. And after that, okay, so the charcoal was frequently used in the royal people and also the Indian people and so on and so forth. And so in the 18th century, the zeolites, that is natural ore, and the inorganic material were found. And in the 19th century, this material was synthesized. And after that, the scale up the synthesized. And so this contributed very much to the current petroleum industry. But in the previous slides, I told you it's a big issue for our future. To solve our issue, zeolite and charcoal are not enough. Okay? So we have to establish one new type of material. That is my motivation. So today I'm talking about the new type of porous materials, and by using this, we try to solve the various issue. So I'd like to ask the question. This is a porous material. Looks like regular structure. How you can make? nanoscale, nanoscale. And macro scale like this is in Japan, in Kyoto, the very famous temple, the Kiyomizu temple. And this is the balcony, the famous balcony. This is constructed using the 139 pillars of Zircova. In this case, no peg was used, no peg were used. Okay? Macro scale, very easy. Still this case, just think about this. This is a toy, but in this case, we use magnet for the connecting to component. So, nanoscale, we are very lucky. We have a very powerful tool that is the coordination bond. Coordination bond is a bond between the metal ions and organic molecule. Okay? So, by using this bond, we can establish this kind of the expanded connectivity. So this is the one example. The gas molecules are assembled in this fashion. Okay, in a minute, if you mix these components in solution. So we call these materials in the porous coordination polymers or metal organic polymer, just like a Lego. So look at the 1 micron crystal. This is the porous material, material, and we determine the crystal structure. This is the result. So, and this side is 1 nanometer. Okay, and then this is 1 micrometer. That means 1,000 here, 1,000 here. So totally 1 million channels. In the 1 micron crystal, 1 million channels already you have. So gas molecule accommodated in this way. Okay. So just look at the nanoscale channel system. What's good for us? So that is this case. Just look at this is 1 cubic centimeter, 1 cubic centimeter, just like a dice. Inner surface area is 4 nanometer, centimeter, and then move to the micropore, 1 micrometer pore. In that case, after calculation, the 400 square centimeter. If we look at the 0.8 or 0.6, in this case, we have 2,200 square meters, very large in the surface area here. So the gas molecules are accommodated in this way. The total is 150 cubic centimeter methane accommodated. But the upper case is just 1 cubic centimeter. So the nano size, nano space is very powerful to get this kind of system. This is just like a capsule hotel in Japan. So the surface area in the case of zeolite, as you know, this has a 500 square meter per gram. This is the football field type, but this radiocarbon has half football field. One case is fully given this football ground here. Can you imagine if you have 1 gram of this material, already you have this surface area in your hand. Also, this is very stable to the acid and the alkaline condition and the up to 500 degrees Celsius and the humid case. So this is kind of interesting. So today, I want to show more development about these materials and also the talking about the history. In particular, I heard the students audience. So I want to talk about this. And this is the year and material development. And the first one I call first generation type network structure. This is second generation. Okay. This case, the people call MOF and PCP. And this is the another type of the advanced function, that is the soft crystal. And lastly, the fourth derivation. So just I want to tell you about history. I graduated Kyoto University, and then after that, I got a position in the private university, in the assistant professor to the associate professor, and then moved to the Tokyo Metropolitan University as a professor, and then back to the Kyoto University and our institute right now. So this is very rare case in Japan. Why so? You understand? I graduate the national university, get a job, private university, get a job in municipal university. This is not national. Tokyo or city. Tokyo has a university. And then back to the national university. Another case, I graduated the faculty of engineering. This is the faculty of science, and faculty of engineering. So many cultures I experienced. But anyway, this is another issue. And so, when I was undergraduate students, I strongly inspired by just reading at that time the UC Berkeley physics course just solved. And this is volume 1, the mechanics, the electromagnetic, and this is waves and quantum physics and the statistical physics. I read this one, in particular this one. This one is very simple equation, the probability is completely directed to the entropy. So that means the ensemble, nanoscale ensembles are strongly connected to the macro scale property. So that means the assembly is very important. And second is dynamics, and third space. So these three keywords very inspired me to do the science. And that time this is the Professor Fukui, the Nobel laureate in the quantum chemistry. I was here. Yeah. So on in that time the associate professor, the Professor Yonezawa, like this. But I want to tell you, this is Kyoto University. The faculty of engineering has a very nice tradition, and the thinking, free thinking, and the fundamental science is important. This is faculty of engineering. Faculty of engineering, but all the people think about the fundamental science. Okay? And so, in this branch, there are several organic chemistry, the inorganic chemistry, and the theoretical chemistry. So Professor Fukui, Nobel laureate here, and then there are the collaborators and the associate assistant professor here, and the Professor Yonezawa here, and I am here. So just one skip, and then my senior Yoshino, and he was awarded Nobel Prize in the batteries, lithium batteries. But another organic chemistry is Professor Noyori, awarded Nobel Prize in organic chemistry. So the fundamental science is very good tradition in the Faculty of Science. So, and I moved to the Kindai University, and so this is just a static to the dynamic, okay? Static to dynamic. So during this time, I just stayed in Texas A&M University, where the Al Cotton, he was the very great professor to open up new cluster chemistry. So you are very familiar in the CC bond, single, double, triple bond, but he started this in the single metal bond. This is very usual, the double and triple and the quadruple bond. So we study and this chemistry, and so just this is the origami folding paper you are familiar with. So this is the boat. This is the sail. So it's kind of magic. So please, okay, uh, flip this one and close your eye and open the eye. Oh, you don't have a cell, just you have a ball. Why? This goes to it like this. So that means static, nothing happened for my feeling, but already changed. Dynamics is like that. So we studied this kind of materials, metal bond system here. Okay, we synthesize this one. So molybdenum coordination geometry. Please look at this. Molybdenum EP like this, chloride here. But once just keep just sliding. And so this structure abruptly converted from this one to this. Look at this molybdenum. P is anti-position. This is syn position. Nothing happened. Just change. So this is the dynamics. So I did this one with him. So, but he passed away. After that, he was so great professor. He published 1,600 papers and 2,500 material. The crystal structure was determined, and his family. I mean, family mean the academic family. The gathering and published this kind of the published papers book. And in the preface, the totally 1,600 papers, and our colleagues selected the papers, and the 19th paper is my paper, the previous one. So dynamics is very important. Carl Cotton focusing on the static structure, very much focusing on the static structure. But the dynamic structure is another next step at that time. But anyway, for the young people, and his golden rule is very, very fascinating. So just I translate the Chinese, if you understand. This is the testament, the written in the testament. You have to work at least 60 hours. Maybe you work 60 hours a week, no problem. But the problem is in the next one, this one. Maybe you understand. It's not alibi. And so this is also important. If it is published, not published, it isn't published. Even the Bible to be published will be of benefit. You understand? Without the book of Bible, so such a big expansion not occur. Okay? And I also another one day I made a mistake. He said, okay, you have to correct this. One mistake, no problem. And so I was so excited. And in 10 minutes later, I bring this my draft of paper. He abruptly angered. I made mistake twice. But, okay, so this history and how did I get started? The chemistry of porous coordination polymers, in particular in the MOF. So that's very important. And so, and in the case of network structure, and this started with Kappa 1 chemistry, because in 1959, the Japanese professor synthesized this kind of network structure using Kappa 1 and the nitride ligand. This is the six-fold interfederation, but network structure. And the framework is cationic. So the anion is incorporated in the cabin. 30 years later, the Australian scientists synthesized this network structure. Also similar, Kappa 1 chemistry. And so I also studied this kind of Kappa 1 chemistry. And also Omayagi, he is also the pioneer of the MOF materials. and synthesize kappa 1. All people use kappa 1 ion. This is the amazing. So my history, after that, I synthesized kappa 1 materials. This one, this 1D coordination, one dimensional, 2-dimensional, 3D dimensional. But we can produce a lot of the crystal structure after that. And to get this structure to characterize this structure, we need to get a single crystal. Single crystal. Without a single crystal, we cannot tell anything. So single crystal is very important. Why kappa 1? Kappa 1, monovalent kappa 1 are spherical structure. Just like this. If you want to put the ball in the square shape vessel, easy. But if you have the triangular or other structure, very difficult. So that means the spherical is a keyword to easily get the crystals. So this is the reason. So I was unknowingly digging near a gold mine. You understand? I did this chemistry. Gold mine is the next, very close that time. So this is started, and we already I showed you this is honeycomb structure here. So in the honeycomb, this structure, there was the organic molecule. Yeah. Before this, most of the gas was anion. So it's difficult to remove because the cation anion interaction is very strong. But this case is gas organic molecule. So this is the start my case in the porous material. Okay. Once again, but that time problem because kappa 1 is a positive charge, and also we use the neutral ligand, so the binding is not so strong. So that the problem is if we remove the gas molecule, the structure collapses. That is a big issue. How we can conquer these things. But anyway, the people think that stone house is very stable, even in the wood house. Cardboard house is not stable. So the feeling of the people like this. You synthesize the organic molecule and construct this one. It's not stable. Okay? So this is a challenge. How we can get this kind of system. So the story of part 1, the second generation system, and to go to the Kyoto University after Tokyo, and then we synthesize this type of structure, and we use cobalt 2+. So this structure is very robust, rigid, and gas molecule, even after removing gas molecule, structure very stable. We can carry it out many cycles. This is a good point. And this is episode 1. And due to this paper, anti-band paper, I was invited to the Gordon conference and in organic chemistry. So in that time, big professors are gathering, also the young people. And I gave up my friend told me, Gordon conference is such a nice conference that most of the people are very friendly. But this is not correct. So after my talk, many people against my data. They raise a hand. You're wrong, something like that. Even in the next morning, in the breakfast, it's a kind of buffet style. I eating. So the one guy, I know him, but I don't. He just in front of me and say, you are wrong. And the next person said, this is the morning. It's a happy time to have breakfast. Don't tell this. Just like this. So that means, yeah, that means an accomplice that caught the world's attention later this. That time is not unhappy, but after that, it's okay. When I look back my history, it was very happy because if I gave the very not so important data, nobody has a comment in that place. Okay. Anyway, so the second generation is like this. This is very important. And then, so second generation compounds have various functionalities already discovered here. And the storage is like this. Previously, I showed in the rod and bar type framework, but the reality is like that. So the student sometimes ask me why the guest molecule accommodated. Why? This is happy. This looks unhappy. Why? This is thermodynamic rule. Okay. So this is large entropy. This is low entropy, small entropy. Why small entropy is preferred? Okay. So, for instance, in the students in the playing the outside on the ground freely, how to hold the students and make them sitting. Okay. If you put this kind of sweets, they're happy and come back to the room. That this is very important. What is sweets in the nanoscale? That is the interaction. Interactive interaction is very important. So that means in the framework, we have to put the attractive site to the guest molecule. If you design this one, you can get this molecule in the cavity. Okay. So in the gas storage, in that case, in the magnesium case, in the 0.1 bar, the 20 weight percent CO2 accommodated. This case in the 5 bar, 64 weight percent. This case in the 50 bar, 70% weight percent CO2 accommodated. So in the last case is at the 35 bar and room temperature. This material, if you accommodate the materials in the cylinder, this is exactly equal to the 9 cylinder, vacant cylinder, okay, high capacity. In that time, the BASF, the big chemical company worldwide, and they produce this kind of materials for the storage of natural gas. And that time the cost is very, very, yeah, yes. This is Japanese yen. That means $1. Recently, our startup company set up the new type of the gas cylinder from this one to this very small one, because this has the PCP MOF here. So this is weight 60 kilogram. This is 10 kilogram. It's very, very easy to handle. So we are trying to have the many challenge. First one is to explore the acetylene. Acetylene is dangerous, as you know. At room temperature, in the 2 bar, the abrupt explosion occurs. Even in the safe cylinder, this kind of the explosion occurs. It's very dangerous case. Okay? So we synthesize this type of the framework and introduce the acetylene. This is the pressure absorbed amount of acetylene. Acetylene absorbed in this way, like this. So this is a crystal structure, acetylene in the surface of the channel here. And so the acetylene hydrogen as a hydrogen bonding is free oxygen. So the double hydrogen system here. So that concentration is 0.4 gram per cubic centimeter, but the compression limit, and this is 0.021 gram. So the 200 times larger than the dangerous case, but still stable. So after that, many people are synthesizing this acetylene storage. This is our case. So the increasing more looks fantastic. But still problems for the application. This is a type 1 isotherm. You see, usually you can get this kind of desorption profile. And this case is show this one. Okay, full loading. This shows the full loading capacity. But if reduce the pressure to this position, only this part is usable. We call the working capacity. Working capacity is not so good. If we have this kind of sigmoidal curve here, most of the other solved one can be used. So still this has a problem. So let's go on to the third generation. Third generation is the soft porous crystal, flexible one. So I categorize this in the third generation type. So this is a famous toy. Overman, yeah. Okay. Overman toy. You see, no change about the component, just a network change. So this kind of idea. So, and using first, just I want to show the source profile. The usual case is like this, okay? Our case, I try to get this kind of thing, okay? You see, and the saturated point, no problem. But next one, if you want to use this solve amount, so in that case, in this pressure range, we can use this one. This is capacity. This is capacity. Okay. This type of absorption profile is very important. So we synthesize various type of compound. This is hinge type. You know, the organic molecule has a free rotation site. The other case is just interdigit. And the last one, interpentrate. The same framework is interpentrate. So we synthesize this type of system. Oh, sorry. So all show the sigmoidal curve. That's fantastic. And in particular, in this case, at room temperature, this supercritical gas substance can be recognized with different gate opening pressure. So this is paradigm shift. Most of the people think porous material should have rigid, very robust, stable. No, new paradigm is just a global dynamics. This has a kind of global dynamic. So by using this third generation type system, we look at the storage and separation. And for instance, this is very important to control gate opening pressure. Okay? And we have chosen this type of interpenetrated system. So this interpenetrated system is like this. So usually the zinc and by pyridine and benzene dicarboxylate is used to synthesize this one. In addition to this, we add substituted one, nitro and amine, so mixed structure like that. So we can get very smoothly this dispersed structure of a single crystal. And then this is the just conclusion. And when we introduce the nitro substituent more, the gate opening going to the lower pressure region. If you use in amino group more, going to the higher pressure region. So the optimum condition like this, we discover this one. So this, our materials work at 1 bar to the 1.5 bar like this. So this is very important. So thanks to these properties, the working capacity is the highest in acetylene storage. So next separation. So we are focusing in the global dynamics. Global dynamics means totally change, structure change. But we look at the local dynamics. Local dynamics in the structure framework is maintained. Only this part moving. So you can imagine, look at this movie like that. Okay? Framework, total framework is maintained. And the gas molecule diffuse the presence of the local motion. Yeah. So we think about the new idea using the big cavities are linked by small channel. Okay? Small channel. Okay? Please think about this. And then we put this kind of motion. Ligand is located here. This motion is butterfly type motion. This ligand is dragonfly type motion. So what's happening in that case? So we control this kind of motion using this kind of ligands. Okay? So the time is limited. Just I want to tell you about dragonfly motion. Dragonfly motion here. We try to separate H2O and D2O. D2O is very useful materials, but in the natural water, only 0.03% or something like that. Very diluted. So we have to get this one. But the boiling point, freezing point, bonding energy is very close to each other, very different. Also, you mix the D2O in the H2O, and that time the HDO produced. So 3 components produced. Difficult, very difficult. So this is the 100 years struggling history with the separation. This is discovered in deuterium. And then the Jean Lewis get D2O from natural water using electrolysis. And electrolysis is also used in big facilities, and also this is distillation power using this tower, and they got the D2O. But separation factor is 1.05, 1.02. Even in the modern case is 1.2, big facility. So 1 means impossible to separate. 1 means. So we need to have a new system. That's why we synthesize this type of materials. This is dragonfly ligand, organic molecule. Yeah. So we incorporate this one in the cavity here. This is the low temperature case. The motion is very slow. So that means the diffusion molecule look at the gate is very narrow. But if the temperature is high, the gate is larger than the case in low temperature. So this is result. This is the time and diffusion. So D2O like this, H2O like this. H2O firstly diffused much faster than the D2O. Our materials can recognize these substances. But in the case of zeolite, exactly the same, red carbon, very famous MOF material, Z7, and the other MOF material. So only our compound can recognize this. So just to make long story short, that's this results. And this is the H2D2 separation. This is H2O D2O separation here. So usually the separation factor is 1 to 2. Okay? But our case is 4 to 200. and the operating temperature is room temperature. So this kind of the dynamics, local dynamics, can work very well for the very closely related material, property material. So going to the fourth generation compounds, and yeah, usually I stop at this point, but maybe the audience anytime ask me, and what is 4G? And this morning, my talk, I was asked, what is 5G? Because the mobile phone now 5G. No relationship. So just I want to touch this one. So already you understand, more materials have various type of functionality. So we have a chance to integrate different properties. So this is one idea to accumulate different functionality to one. So and more than 15 years ago, we did this kind of connected system, more for more. After that, many researchers synthesized various types of the integrated system. So nowadays, integration is very popular in MOF chemistry. And so the other thing is with different materials. This is the organic polymer and MOF. And this is the ionic liquids and MOF, and metal MOF. And this is MOF, and MOF and the amines, and this is in particular on the capture of CO2. This is metal oxide, semiconducting materials, and MOF. And the COFs, MOF, and the enzymes, and so on and so forth. So integration is a key word for the future to function materials. So this is Ocean University focusing on the ocean and water issue. So today I talked about the gas substances, but gas substance is much difficult than the liquid solution system. So we can carry out this kind of chemistry for gas substances. That means equally applicable to the solution system, speed and river and something like that. So this is the study in aqueous solution study. Already many people are studying like this. Water, the first point is to synthesize water soluble. So that's very important. So in the water purification and electrochemistry, and this is the heat transformation, or so on and so forth. Many carbon capture and so on. She was my student, and now she's in Thailand. Thailand is struggling with the pollution in the river, and so she is doing the just capture of toxic heavy metal, arsenic, mercury, and cadmium. So, and also the lithium is a very important battery. So the recycling the lithium is also another topic. And this is the startups. I don't know the details, but I heard this startups, Puerto Rico, have a system to synthesizing, having more materials for lithium recycling. So, and the fourth generation means this kind of application, more and more application. And today I have no time to introduce the slow release in delivery for our life body, but this is just very fascinating. And this is startups in the world right now in the over 40, and including maybe I cannot count the Chinese startups. If I count this one, somebody said, and over 100. startups already for the MOF material. So that is the good news for the doing this kind of applications. And the fundamental chemistry shows from the robust chemistry to the flexibility, and the conversion, hybridization, and so on and so forth. But these can be applied to that case. So to stop to end my talk, just I want to tell something, just relaxing time before end. So the last year, I was selected as a Royal Society foreign fellow. Royal Society fellow is a kind of academician in China, and so I attended. And what is interesting is this is a charter book in about 370 pages, because the Royal Society was founded in the 17th century, already 370 years. So every year, selected people make a sign in the audience of the fellow Royal Society academician. So this is a charter book. So I have to obey this kind of rule. Mostly the contribution to the society, people. Yeah. And but anyway, to sign signature here. So this is not a true paper, very sleepy. So only one exercise. Then I did this. So, but anyway. So I may, yeah, I did. So you can see. And so I put my Chinese character also here. But anyway, so what I want to tell, this is the Isaac Newton. And the other case, this is Max Planck, the quantum chemistry, quantum physics. And this is this. He was also this signature. Yeah. So lastly, so my motivation anytime, and also the discovery is very important as an experimentalist. So the students in the everyday do experiments or something like that, and you discover. So you are so excited. Professor, I discover. But mostly not so interesting. Not so interesting. If this discovery with wonder or surprise, that is interesting. But you see, in the maybe this Chinese character, Chinese, you can understand. I hope. For instance, in the mathematician solve Fermat theorem something 300 years, nobody solved. But people, oh, wonderful. They don't understand. But wonderful. But in the chemistry, we discover with wonder, the people, oh, like that. You have to get this kind of the inspiration for the people. So that is important. And also this is very DWI. DWI is very important spirits doing the experiments. So before this, I write down something, okay, on your signature book. This one. So, but this is very important. So I made the beer glass, and when I retirement in the 65 years, the Kyoto University retirement. After that, I was appointed as distinguished professor, and I can extend my position. But retirement age, in 65 years old, that was a big party. All the people gathered. I gave this glass. This contains discovery, wonder, inspiration. Every day, drink beer, looking out this one. Okay, so this is the beer glass, and the other things is I like this the Chinese, and this one, and our alumni club is this one. The I I I, I cannot pronounce Chinese, so Japanese case. Yeah. So this is my motivation. Almost the finish. So, yeah. Yeah. So thank you very much for your kind of me.
Okay. We thanks the Professor Kitagawa Sensei. His great report. I think his report gave us a brief introduction about PCP MOF and gave our students a basic lesson about the framework science. His report explained profound theories in simple language. So please feel free to raise questions if you have. This is a very valuable chance to communicate with Professor Kitagawa Sensei. Who have put your hands?
Thank you very much for your wonderful lecture. I have a question to ask that, as we all know, the gas storage, like hydrogen storage, is a very important energy issue. But for a long time in the past, the scientists have been committed to using PCP to storage the hydrogen, but still cannot meet the needs of practical applications. So I want to know, do you think it's necessary to continue to carry out the related research? Thank you.
So yeah, good point. And hydrogen storage is the last part, the gas storage. And so in my slide, you see it's just a suite, the student suite. In the case of hydrogen, this hydrogen has in the surface actually very weak. Suite is not enough. So another idea is needed, required. So maybe this may be a dynamic structure point of view, very important.
Any question? Any question?
Good afternoon, Professor. I'm also engaged in the applied research of, related to MOFs. And from the papers or literature I have read from now, I have found that most research is on the basic of the structures, such as some classic MOFs, which has already synthesized. So I want to know, do you think it is necessary to synthesize a new structures of MOFs in the current situation, or it is more important to explore new application of older structures?
Okay. Okay. So and at the beginning of this chemistry, many people try to get new structure. This structure, new structure. But right now, the 90,000 materials already synthesized. So if we want to get the new structure, still you can do this, but the most exciting things is new functionality. So just think of the new functionality. For instance, he asked hydrogen storage, something like that. And think new function and design framework, design the interaction framework, and synthesize. If this is the new materials, both new material synthesis and new functionality, it's fantastic. But maybe getting function best.
I got it. Thank you. Thank you.
I'm not in the realm of chemistry, so my question will be related to the climate because I'm a student major in physical oceanography. So my question is that we all know that green gas serves as a major external force of climate system, and the greenhouse gases contains various gas with different chemical and physical properties. So you mentioned that MOFs can be a useful material to keep such GHGs in a stable condition to keep from the atmosphere to achieve the goal of carbon capture. So I was wondering that if there's a universal material that can absorb all kinds of greenhouse gases, or we must choose different materials to absorb every single kind of greenhouse gases. Thank you, Professor, for your very heuristic speech.
Yeah, CO2 capture is very important.
But something like methane is also important for the greenhouse effect. So I was wondering if there's any MOFs that can do that kind of absorption as well.
So yeah, the just last 10 years, people just hate CO2. But my message is, why don't you use CO2 from the air? Okay. Yeah. CO2 is a carbon resource.
I got that. Thank you for your answer.
Thank you, Professor. I have a question about the third generation MOFs, like the dragonfly structure. So you are suggesting that the linker is kind of rotating, right? So vibration. Okay, I see. So all the linker will vibrate randomly, or just they will follow some kind of pattern. So what's the driving force for the motion?
Yeah. When you synthesize the organic molecule, for instance, in the phenyl group is connected like this.
Yes.
This has a rotational motion.
Yeah.
And my case is just synthesizing this one. This. So this is a little bit move like that.
Oh, I see. Okay.
This is butterfly type, dragonfly.
Yeah.
So we use this.
Okay. Thank you, Professor.
Thank you, Professor Kitagawa, as a nice talk. I have one question about how to design and synthesize the MOFs with good performance as we want. Probably AI may give us an efficiently way to design.
Yeah.
What do you think about this?
Yes, and just I said, in the 90,000 MOF materials so far synthesized. So if AI run 90,000 structure, this AI will advise us very good framework. Yeah, I'm sure. And so the the point is even so, still not enough for the creating because the synthesis is the many body problems. We use solvent, ions, temperatures, just everything. So based on this suggestion, it's a suggestion. So we just improve more or do the experiment right now. But I don't know that 20 years later, 50 years later, I don't know. But
Thank you,
you are young, still you are alive.
Okay, thank you.
Okay, any question?
Good afternoon, Professor. I see that more flexibility is mentioned in your report, but the flexibility is a dynamic molecular skill behavior, and the relevant characterization is very scarce, which is disadvantageous for mechanism research. So I want to ask that if you have any questions about this.
Maybe your question is how to characterize this kind of the complicated emotion, something like that. Okay, yeah. Today I did not talk about this. We determine the crystal structure. Of course, the crystal structure is a static. Then we add the computer calculation, simulation, also quantum chemical calculation. Also how the molecule diffusing and what kind of interaction in this kind of motion. So as a total the results, and we discuss about it. Okay.
Yeah. Thank you.
So anytime the research is like you synthesize new type of material, you discover new function, high absorption, separation factor. So you need to do the characterization.
Yeah.
Using the computer or solid state NMR, crystallography, sometimes the singleton radiation facility to determine the crystal structure in situ. In situ means just add gas structure change. You can. This kind of methodology very important.
Oh, thank you.
Okay, due to the time limit, if you have more questions, we can communicate with Professor Kitagawa Sensei after the forum. So, good afternoon, students, members, and my friends. Today is a good day. It's a great honor to invite us, the very famous and well-known scientist, Professor Kitagawa Sensei, to our university for communication. This lecture is also celebrating the 100th anniversary of the founding of our university. Firstly, we would like to give my heartfelt thanks to all those people who come to listen to the lecture. Then we thank to the organizers, thank to the Academy of Future Ocean, thanks to the Deng Li, Deng Gan, and others. Thanks to the Academy of Chemistry, thanks to Deng Bao and other members who devote much time to this lecture. Especially we thank to Professor Kitagawa Sensei. It's a long journey from Kyoto City to Qingdao City. Although the journey is long, but our friendship is very strong. There's one thing in China said, if you don't know Professor Kitagawa Sensei, even you have download MOF works, it's like close to zero. 用中国话就是 金庸里小说里的话，就是文人不识陈近南，我就是变成英雄也枉然啊，就是做帽夫你不知道北川镜，做尽帽夫也枉然，就这个意思。Professor Kitagawa sensei, it's we want to thank Professor Kitagawa sensei. I believe many people at Sun maybe do some MOF related works, but very few people know who was the #1 person to construct the MOF PCP science, who to work from 0 to 1, and to construct the new science in chemistry. Yes, it's Kitagawa sensei. We hope more sensei can come to Qingdao City and to our university MOF, and hope more communication with Professor Kitagawa and more possible cooperation between our university and Kyoto University in the future. So I propose put your hands and give a round applause to Professor Kitagawa. Thank you, thank you. ありがとうございます。谢谢。The work is the lecture is done. Thank you for listening.
Thank you, Kitagawa-san, for your very impressive talks. And I'm not in this field, but I do feel your passion for science. And I think that's the most important for doing research. And also, I think your pioneers' discoveries has give us the wonder and give us the inspiration. Thank you very much. So on behalf of the AFO, and I would like to extend our sincere gratitude to you with a very special gift. It's a special designed dish which is decorated with seashell. And the seashell is with the 5-4 squares. I don't know if you have with 5-4 square, which is the landmark, the city landmark in the city. If you have time to go to 5 square. Thank you.